Hello, everyone. My name is Kyle Fries. I'm the epidemiologist for STC Health in Phoenix, Arizona. We put together a short lecture series on the epidemiology of pandemics and how it fits in with the larger picture of COVID-19. We have, like I said, 4 parts. I'm going to talk about some of the epidemiology that we used during outbreak investigations, some history of pandemics in general, and then we're going to dive into COVID-19. I'm going to show you some of the broad data that's been available since the outbreak started. And then I wanted to finish up with some lessons and recommendations on how we can move forward as individuals and as society. So, like I said in part 1, we're going to talk about some basic epidemiology terms. And with that, let's get started. First thing I wanted to start with was to make a distinction between 3 common epidemiology terms. And those are something that is endemic to a population, and then an epidemic, and then a pandemic. So to start with an endemic, or something that is endemic within a population, what this term means is a constant or steady level of disease in a population above the expected norm. So something like malaria in areas of sub-Saharan Africa or in other tropical climates, something that is existing above the expected or normal level. And then also in the United States, surprisingly, obesity is sometimes called to be endemic, even though it's not infectious per se. Conversely, an epidemic is something that exists in a population above the normal expectancy, but exists more in spiking levels. So you can think of a curve. An endemic is something that just kind of hangs out above the normal expected level, but then an endemic, you see these larger spikes is what you're seeing with COVID-19, for example. But a more popular example is something like a cholera epidemic. You see a really large spike and then kind of a tailing off as time progresses. And finally, a term everyone's heard a lot recently is pandemic. What a pandemic actually is and how it usually is defined is fitting the following 3 criteria. So there has to be an emergence of a new strain or a new pathogen. That pathogen has to have the ability to infect humans and cause severe illness. And then finally, the pathogen has to be easily spread amongst humans. Examples of this are the 1918 Spanish flu, which has been in the media quite often. I'll cover that a little bit. I think in part 2 of this. Also H1N1, also called the swine flu, that was back in 2009. And then of course, as of the 11th of March of this year, COVID-19. Looking at these 3 bullet points, you can see how a lot of epidemiologists were pushing to have COVID-19 labeled as a pandemic earlier on. There are many outbreak measures that we can look at. These are just 2 examples. The first broadly is the attack rate, which is the number of new cases of a disease in a given time period over the number at risk at that time period. So again, pretty straightforward. This is just the number of new cases divided by the at-risk population. So it's up to the epidemiologist to define both the denominator and the numerator here. Going a step further, we look at something called the case fatality rate. This is sometimes called the crude death rate or crude mortality rate. I think case fatality rate is the most seen in the epidemiologic literature, and the one I prefer to use. This is just saying that of the number of new cases or confirmed cases of the disease, how many of those result in death? So again, this is up to us to define the numerator and the denominator. 2 things to keep in mind for both of these equations are we have to have a really strong agreed upon case definition, and which is one of the problems that we've had with COVID-19 is the number of testing that has not been done. So both of these are kind of hard to get a really reliable measure of. But regardless, we need to have a really good case definition that's established, and then also we need to define our time period very carefully. I want to wrap up this little part of the lecture with a quick example of what a disease outbreak can look like. Now, this doesn't apply to every particular pathogen, but I wanted to provide something that was very similar to how COVID-19 came about, and we've seen it in other pathogens as well. So in many cases, pathogen exists in animals, doesn't cause fatal disease, so it's able to propagate and eventually become skipping species. In this case, for COVID-19, it was able to jump from what they think was bats into an index patient or a group of patients, which is how the spread begins in humans. From here, there's another term that we use, something called the R0. Simply put, this is the reproducibility of the pathogen. So for an example of something that spreads between humans, an index patient can spread the pathogen to 2 more with an R0 of 2. Then each of these patients can infect 2 more. Each of those patients can infect 2 more, and so we go. This is how we end up with that kind of exponential curve that we were seeing with COVID-19. Now, something with R naught that I want to mention, each pathogen has a unique R naught that we learn as a disease progresses. So something like seasonal influenza has an R naught of between 1.5 to 2, depending on the area and the study that you're citing. Um, but something like malaria, although it's not spread amongst humans in a highly endemic area, like I mentioned, some with sub-Saharan Africa and some tropical climates, you see a huge range of R naughts, all the way from 1 all the way up to 3,000. In relation to COVID-19, we think that the R naught is hovering somewhere around 2, maybe a little closer to 1.8. So what I show here in this graphic is pretty accurate based on our understanding at this current point on how contagious or how this is reproduced throughout a population from generation to generation. Then one final term before we wrap up this little mini lecture is the concept of herd immunity, because it does relate back to the R naught of a particular pathogen. Herd immunity is the amount of the population or the percentage of the population that needs to be vaccinated or have some sort of immunity to protect the rest of the population for those that are not able to have immunity or vaccination. Young people, old people, immunocompromised people, things of that nature. So this equation is simply means that V is equals 1 minus 1 over R naught. And that gives us the percent of the population that needs to be have immunity for the rest of the population to be protected. So that's a real quick rundown of outbreak investigations. If you're interested, please contact me for additional resources. But in the next series, in part 2, we're going to talk about some of the history of pandemics over the past 200 years. So we hope you join us. Thank you very much.